Okay, folks, we're back into the guts of technology now, hopefully, with an introduction to NoSQL, or perhaps not only SQL. I will leave it to Joe Drumgoole from MongoDB to tell us a little bit more about that.
Hi, folks. My name is Joe Drumgoole from MongoDB. Apparently it's going to take... Oh, no, look. Boom, straight away. I just wanted to ask the audience before I got started, who here has ever actually managed to get some data out of a relational database using an SQL query? Can I have a show of hands? Okay, that's good. You won't be running out of the door screaming when I get started. My job in MongoDB, and this is the only thing I'm going to talk about MongoDB, is to help partners become successful with our technology. So if you're interested in MongoDB at all, do come and talk to me afterwards. Other than that, I'm trying not to make it a company pitch from here on in. I wanted to start with a little history lesson. Anybody old enough in the sector to recognize one of these? This was the hot disk product in about 1987. This is a digital RA82 disk drive. It's actually about that size, about that wide, and they used to come in racks of 3. And when you stack 3 of them together, it was 2.4 gigabytes of disk space. And it cost $66,000 for that much disk space. Basically, my USB key, if I could transport it back in time, would make me basically a millionaire. And I want you to realize this because this is the same time when we were really starting to get into relational databases. And one of the things about relational databases is they were all about the disk space. And the company that built these, Digital Equipment Corporation, who was one of my first employers, was the big data player of its day. It ran most of the internet news sites around the world, which is what passed for a social network in the early 80s. It was huge. It's where you went to find stuff out, you asked questions, you got replies, you got flamed. All that good stuff we have in the bottom half of the internet today happened on the internet news networks in the early 80s. Great company, gone now, for lots of good reasons why. And then look at these guys, right? This is Ken Thompson and Brian Ritchie. These are guys that wrote the Unix operating system. And the Unix operating system is the operating system that we all use today on all the Apples we have around the world. They call it something different, but it's directly derived from what these guys did. And they're working again on a big deck computer, a PDP-11. These guys were the smartest programmers of their time. But when they wrote Unix in 1970, they were effectively clerical workers in AT&T. They were smart clerical workers, but they didn't get paid a lot of money. They were doing something they loved, but they were in the great mass of people who weren't in AT&T to help with the telephone system and therefore were almost secondary employees. These guys built all the technology that we're going to use, but they were cheap. Now, they've gone on to be, Ritchie has passed away, but Ken Thompson actually works in Google now and has written the Go programming language. But in those days, they were basically cheap guys. And I want you to understand that that's a curve we've gone through. One of the things that's changed in the world is that now storage is really cheap and programmers are incredibly expensive. And these are the 2 economic drivers that are going to set the stage for what you're about to hear about NoSQL going forward. Another guy from the 70s, a guy called E.F. Codd, he invented the relational model. He didn't build the first database, he just designed the model and the programming and the algorithms around it, the idea of a relational table and relational calculus. He built that in the 1970s. It didn't really pick up again until Oracle and Ingres picked it up and started building technology around it in the mid-80s. And we've been doing data the same way ever since. Every single company in the world has a relational database today. Every single company in the world today uses relational databases to store the mission-critical data of their businesses. And it's fine. Traditional data approaches have a very simple model. Storage space is scarce and finite, and therefore we follow a very simple model. Filter, as in, I can only put so much in, so I'm going to choose the data I put in. Store, put it in the database, put it on disks, and then I'm going to distribute it to the rest of the company through applications, through emails, through web pages, the whole thing. And this is a very traditional model of data storage that we've used in encyclopedias and newspapers and libraries and banking, which say essentially storage is finite. I only can put 12 volumes of Encyclopedia Britannica on your bookshelf. I can only distribute a newspaper with about 30 pages, and I can only distribute that in 1 or 2 cities. I can only put a fraction of the books published in any library. I can only keep a small subset of your data. Why? Because there are caps on storage, and I don't just mean physical caps in technology terms. There are physical caps in real-world terms on storage, and there are bandwidth caps. I can only ship so many newspapers. I can only ship so many Encyclopedia Britannicas. These caps defined how we did data in the past. So what's happened in 2006? Well, a couple of things happened you might not remember. North Korea tested a nuclear device, and we're still all here, so, you know, Cold War, longer it goes on, the longer it'll go on, which is great. Italy defeated France in the World Cup. I can't remember what we did in that. Pluto got demoted to a dwarf planet. 2 businesses launched. Twitter got launched, and we all know what an enormous success Twitter has been, and they've just launched a brand new data storage service called Manhattan this week. But Google bought YouTube for $1.65 billion and essentially said social networks are big business. They actually defined the starting point for the social networking craze. And what was YouTube about? It was the biggest store of data ever created. It was capturing enough video every day to equal the total output of the PBS TV station since the time it started. The other thing that started with little less fanfare was a business service called Amazon's S3 service. This was the first of Amazon's web services. S3 was a game-changing event for the technology sector, although very few people realized it at the time. What was disruptive about AWS? It took storage from $5 a gigabyte down to 15 cents a gigabyte per month. Now, I know this because I started a backup company that year, and our original business plan said, in year 2, spend $1 million on storage in a data center and buy a bunch of hardware from IBM or EMC or some other massive storage vendor. And I'd done the maths. It was $5 a gigabyte per month. That's what it costs us, total cost of ownership. So I literally went cock-a-hoop when AWS joined, as did a whole bunch of other people, because it was like, I could take all that capital expenditure and buy chocolate with it. I didn't need to spend it on my business anymore. And it gave you unlimited storage. And I mean unlimited. There was never, ever going to be a cap again. In fact, it caused us huge problems in my business because we had a little backup program that went wild, and it just wrote hundreds of terabytes of data into S3 without us realizing it. But you could purchase the storage in tiny chunks, 1 gigabyte chunks, and you only paid for what you used. And I think 15 cents a gigabyte versus $24,000 a gigabyte only 20 or 30 years earlier. So this was a big disruption. What did it mean? No CapEx, no data center required, and the availability of Google scale to businesses, the ability to go large when you needed to at utility pricing models, which is to say, I didn't go from this point to that point by spending $1 million in one big chunk. I went by spending $1 at a time, and I could amortize that against the large number of users I gathered in. So we went from filter, store, distribute to a brand new model. Store, filter, distribute, which is store everything, not just a little bit of your data, not just parts of the information about your employees, not just the last 2 years of what happened on your social media or your e-commerce site, but everything. And once you have it all, then you can decide what's interesting or valuable to you. And of course, distribution now is free because everybody has global distribution. The internet has enabled global distribution for every member of this audience at, again, cent pricing. But store everything's a huge challenge. SQL databases were not designed for that. They were designed for scarcity. They expect pre-filtering of information. They expect that you pre-filter and then have an order and an organization of your information. Jason talked earlier on today about data being dirty. Well, a lot of the problems of getting data into an SQL database was getting it clean first of all. It assumed monolithic memory, and by monolithic memory I mean memory that's contiguous on a single machine. That's expensive. You end up with an IBM Z series mainframe if you follow that route all the way down to the end. It wants a single disk farm on local network storage. It's really hard to partition, which is to say, if I wanted to split it up, I'm not sure how to do that. And it's based on 1970s storage assumptions, which is storage is really expensive and programmers are really cheap. This was a real problem for Google. Their search index in 2010 was 100 million gigabytes. And they were adding 100,000 gigabytes of data a day. They were doing the store everything for all of us. They were taking a copy of every single piece of data on the web that their spider could get their hands on, bringing it into the Google grid and doing the filter and distribute later. The databases they could use for this problem did not exist. There is no database. If you took the top 10 databases on the Transaction Processing Council's database mark, it wouldn't even come close. Just to give you an idea of what 100,000 or 100 million gigabytes is, if I took 250,000 MacBook Pros, stacked them 4.1 miles high, that's what 100,000 gigabytes of storage, or 100 million gigabytes of storage looks like. So why NoSQL? With these data volumes, we're talking about three things. Velocity, which is the ability to get this stuff in really fast or out really fast. Variety, we're no longer dealing with tabular data, text and numbers. We're dealing with video and images and unstructured text like the stream of logging information or variable sensor data. And lastly, and actually volume isn't the biggest challenge, lots of it. Although most businesses today are really only in terabyte scales of data. We haven't hit petabyte scale. Yes, if you're Verizon in North America, you've got petabytes of data. Yes, if you're Vodafone, you've got petabytes of data. I guarantee you, and Jason echoed this, everybody in this room has a terabyte scale problem for data. And I'm not the only one that says this. Gartner says the same thing. Of the way that we break up data, it's about diversity and real time is the real challenge for people. Actually, only 15% of the respondents to this Gartner survey had more than 100 terabytes of data. So, I mean, it's not a big data problem in terms of the size and volume. It's a big data problem in terms of volume and velocity, or variety and velocity. But storing all this data is not the only challenge. You need to get it in, get it out, and do things with it. The key to unlocking your big data is NoSQL technologies. And so I'm going to take you through some of the basic models we use in NoSQL for unlocking this technology. The fellow following me from Cloudera is going to talk a lot more about Hadoop, which is one of the key tools in this arena. I'm going to talk a little bit about that at the end, but I think you should stay for that talk. Cloudera are a great partner of ours, and Hadoop is a fantastic technology. So what is NoSQL? What's the goal of a database? Data durability. It's got to stay in there once you put it in there. You've got to have consistent performance. It's got to basically perform the same way under lots of different workloads, under changing workloads, under different sorts of queries. And it's got to degrade gracefully under load. As we increase the load, it shouldn't jump up and down. Yes, all databases have a point at which they will fall off a cliff, but most databases should go up and then peel off gently. The challenge with big data workloads is they require distributed computing. And distributed computing is just a code for divide and conquer. Two of the things it's very hard to do in a distributed computing network is transactions and joins. Transactions is the ability to say, I want everything to happen all at once as if it happened all at the same time, even if there's lots of things going on in the transaction. That's really hard to coordinate across lots of different systems and have these consistencies of durability, consistent performance, and degradation. And joins, where I'm bringing in data from lots of different tables to produce a new view or a new table. So our founders, Dwight Merriman and Elliot Horowitz, who actually the people that built DoubleClick had this problem in DoubleClick and decided they could only build a NoSQL database without these properties and make it successful. Turns out they weren't the only ones. There isn't a single NoSQL database in the market today that offers just transactions and joins. The way you do that, you move it up into the application. The application has better knowledge of this. So distributed computing, just a quick breakdown. It's a divide and conquer model. What do? We take that big monolithic database and that big monolithic lump of memory, we slice it up, and we essentially partition the load across all those different machines and all those different disks. And that means when we make a query, we can farm it out to the different disks, aggregate the results back. Every single NoSQL database does this. They do it in different ways, but this is the essential model. Some of them don't have a master, and that's okay. So it'll happen that the compute node you connect to first will be your master for your queries, but they all use the same basic model. And that's how you get the linear scalability, and that's why Amazon becomes so powerful, because you can continue to add nodes to add capabilities and power and performance to your distributed environment. You're going to hear 3 common types of NoSQL: key value stores, column stores, and document stores. Key value stores are the kind of basic entry-level thing. Column stores, I'm going to talk about. Document stores. There's also lots of hybrids of these types. I'm going to go into each of these in order. And there's another term you'll hear called NoSQL. NoSQL is essentially SQL vendors trying to get in on the act by offering NoSQL-like capabilities inside relational databases. And that may work for a lot of people. I'm not going to talk about those vendors. And there's also a thing called graph stores, specifically for storing graph data. I'm not going to get into those guys either. I'm going to focus on key value stores, column stores, and document stores, because right now they are the hottest properties in the NoSQL space. So what's a key value store? It's a very simple thing. It's like a dictionary or an index. Think of the index in a book if you're not familiar with the technology. It maps keys to values. So an index tells you where words appear on a page. You can find one word and get the pages it's on really quickly, right? It's a single index. We don't have multiple indexes for most books. It's very fast. It's, and imagine the same way that you'd have to flick through a page of a book rather than looking in the index, you get in there very fast. Think of it as memcache, for those of you who are familiar with memcache, on steroids, which is to say it's not just in memory, it's also persistent on disk. It's great for things like shopping carts and user profiles. So I want to get Joe Drumgoole's shopping cart when he logs into Amazon, and Amazon have built a NoSQL key value store exactly for this. The minute I log in, the first thing it does is gets my shopping cart. Gets a bunch of other information, but they know the most important thing for most users is the shopping cart. And it's just a Joe Drumgoole, his username is J Drumgoole, look up J Drumgoole, here's his shopping cart, boom, it comes straight back. And it comes back, no matter where I am in the world, in sub-millisecond time frames. It's also brilliant for user profiles. Get the rest of the information about Joe, his locale, his location, etc. It's really inefficient for aggregate queries, though. If you want to find out all the carts with $100 worth more of goods, you've got to look at every cart. And I don't have that list of carts unless I've already created it as another element of the key value store, where there's a key which says all the carts. And guess what I have to do when I add a new cart? I have to update that key value store as well. So it's very good for discrete data. It's not great for getting aggregate data, the classical, what we call a classic query in a relational database model. Select X from Y, where Z. The next one I'm going to talk about is column stores. And column stores are trickier for most people to get the hang of. I spent several days on this week. Instead of slicing up a relational data as a set of rows, it stores it as the columns, because it makes column indexing and column reach much more efficient. I've got some pictures to show you how this works. It's great for column ordered operations. It's not so great at row-based queries. Let me just show you. So relational and row order databases materialize the storage as rows, which is to say they take each row, which is fixed length, and they drop it in one after the other on disk. And that means I can retrieve whole rows really efficiently, and I can find whole rows by essentially saying, if I need to go to the 500th row, I seek the row length times 500, and I can get to that point on disk very efficiently. It's a great way if you need to get the row data out really efficiently. Column databases pivot that model, and they store the data as lists of columns. And it's designed essentially for you to get the column data. So it's very efficient to do things like saying, sum up all the data in a particular column, or tell me all the basket values, or tell me a list of all the users that are currently logged in. Relational is great for queries that return small subsets of rows and need all the row data, i.e. find all employee data for all employees with salary over $12,000, because I want to report with all the data for each employee. When you're using all the row data, relational is great. Columns are great for data that just requires that column of data. If you just wanted the salary data on a very large employee table, you'd have to pull out every single row to get just that column. But in a column-oriented database, you just retrieve that column of data because it's already in memory and stored, and you can do the summation function on that very efficiently. So give me the total salary outlay for all staff can be done very fast in column-oriented databases. Then the last type I'm going to talk about is document-oriented databases. Document-oriented databases store their data as JavaScript. JavaScript is a programming language we use in browsers, and it has a corresponding object format in text called JavaScript object notation. It's essentially an associative array of key value pairs. The values can be documents themselves, so you can nest a document inside another document. The values can be arrays, so you can have lists of numbers or types or strings. And within the arrays, you can also have documents. And the data is implicitly denormalized. One of the things we've learned about in relational databases is splitting everything up into fourth normal form is great for storage on disk, but disk is cheap. Actually, denormalizing makes data access much more efficient. So in document databases, we essentially use sub-documents to bring the data that we want to be together in the one place. And that means when I retrieve a document, I get all the information. I don't have to do a second seek to disk. Documents are easier to understand and easier to program to. Here's a relational model of car ownership in a table format, and here's the same thing in JSON or JavaScript object notation. I think it's easier to read the document, and it's much more correlates with how programmers think about the world, because it exactly maps into the objects in their programming language. We talked about agile programming earlier on. One of the key things about document databases is because they're so close to the programmer's model of the world, there isn't this horrible unshuffling and reshuffling of data to get it into relational format. As a result, we've seen projects where relational models have tried and failed for 3 years to be successful. We've delivered the same project in 3 months using an agile approach and using a document database as the underlying technology. And document DBs are full-featured. They're not just key value stores, they're not just column-oriented. They provide a rich querying interface, including things like geospatial, text search, the ability to aggregate data through pipeline queries, and a basic map reduce function that allows you to divide up and conquer and process your data in groups. So where does Hadoop fit in this framework? Well, Hadoop is a map reduce framework. And I'll give you a quick intro. It'll set the stage up for Cloudera. Hadoop is for when you want to look at all of your data. Like a database, no matter who they're selling you or what they're selling you, a database is really optimized for retrieving subsets of the data. The query should not be returning the complete database because you end up with a table scan. Table scans are horribly inefficient. You've got to walk the whole table. When you want to look at all your data, and a classic look at all your data challenge is something we're all familiar with, counting votes in an election. What do we do when we want to count votes in an election? We don't sit one person down and have them count all the votes. He'd be here for the rest of his life, or she would be here for the rest of her life. No, we divide and conquer. We get lots of people to count the votes in parallel, and we sum the results. Well, Hadoop allows you to do the same thing for data. divide your data up, do a simple processing function on each piece of it, aggregate, but here's the real trick, then do something different again. So you can count all the links of all the web pages in Ireland, then count all the links of the web pages in Ireland that are in Roscommon, then count the ones in Roscommon that point at Northern Ireland, and you can feed that data backwards into the same Hadoop processing loop. Makes it really easy to do large data processing on huge data sets. Again, as Jason said, there are very few companies that really need Hadoop. Most people can get away with a good database, whether it's NoSQL or relational. So let me talk for the last 2 minutes about a mature NoSQL model. What we see with businesses that have started down this line 2 or 3 years ago, they have 3 separate sections. A front end, which is a very low latency, high performance, bespoke database. The 2 I know about is one called KDB, which is used by a company here in Northern Ireland called First Derivatives to do very fast, complex event processing in the financial services markets. In the middle is a general purpose NoSQL database, or often now a relational database, that does all the basic processing you want to do on all your generalized data. And then at the back end, you're going to have Hadoop for deep analytics on large data sets. Now, most businesses won't need all 3 layers, but everybody's going to end up with 2 of these layers going forward. I think for most of the people in this room, you're going to end up with that middle tier and that back end tier. The front end stuff is for very kind of specialized cases. So, in conclusion, this is one of the great technical transitions of our generation. SQL has ruled the roost for 40 years. It's changing. Everyone in the room here is going to have a NoSQL database at some point in the future. It's worthwhile investing in some learning and knowledge. There's lots of material out there. Right now, these coexist with relational. Almost 100% of NoSQL deployments sit alongside an Oracle or an SQ or a DB2 database or a Microsoft SQL server. In the future, we see this replacing relational. Why? Because it's just easier to program to than relational. And it's all open source, so the price of admission is $0 down. You can get started today with all of these technologies. There isn't a single NoSQL vendor out there that I'm aware of that has actually closed source technology. And if you want to ask me specifics about MongoDB, I can talk to you about it afterwards, or indeed any of these other NoSQL vendors. And we're done.